Energy neither be created nor be destroyed. Energy is a conserved quantity. Or is it? From the very beginning of our high school, we all have heard of conservation laws. They are all around us. But why do they work? And from where they came from? And how do we know they are correct? In this video, we are going to talk about a theorem which tells us why conservation laws works. We are talking about Noether's theorem. Noether's theorem is a theorem given by EMMY Noether, which is a great mathematician. Noether's theorem tells us that conservation laws are the outcome of the fundamental continuous symmetries of the universe. That means conservation laws works because there are symmetries, because there are such symmetries which is not broken. If the symmetry is not broken, conservation laws would work. Okay, let's take some examples of some conservation laws and their symmetries. Let's take an object which is moving in space. It doesn't matter where the object is located. The physics would be working the same way regardless of where the object is placed. For example, if the object is moving here with some velocity, it doesn't matter if its coordinate would be here or here. It will be moving in the same way, or the outcome would not be different, or the physics would be working the same way. The process is symmetric under spatial translational invariance. What does this mean? It just means that with change in spatial coordinates, the physics are not changing. That means the outcome would be the same, and everything that is happening in this coordinate would be happening in this coordinate. There is nothing different except the coordinates. Okay, so let's take another case of a object which is rotating. If it doesn't matter if it was oriented like this or this, they are rotating in a different orientation, but the physics would be working the same. But it would not be the case if they are in a gravitational potential. Then it matters how they are oriented. Okay. The symmetry associated with this type of rotation is called rotational invariance. That means with changes in rotational orientation, the physics is not changing, and the associated conservation law in this case is angular momentum. In the previous case, where the object is moving in spatial translation, the conservation law, that is linear momentum, and in this case where the rotation is involved, it is angular momentum. Okay, so why energy is not conserved? The symmetry associated with the conservation of energy is time translational invariance, which looks some kind of very tough thing, but it's just easy. It just means that with change in time, that means it doesn't matter when the event takes place, the physics is the same. It just matters that if the universe is time translationally invariant, it just means that it would not be matter when an event takes place. The process would be the same. The outcome would be the same. Our universe is not like that. Our universe is not symmetric under time translational invariance. For example, the universe is expanding. When the Big Bang happened, after the Big Bang happened, the universe is continuously expanding more and more. Every point in our universe was expanding more and more, more and more. Every point from every other point is moving away, and it doesn't matter that any two object is moving. No, the space between the objects are moving relatively expanding. The space is expanding, and the space can also be warped, and the space can be curved, as we have all seen from the general theory of relativity. So because of this extreme changes in the curvature of space-time and the expanding of space-time, the time translation invariant symmetry is not symmetric in our universe. An example would be the cosmic microwave background radiation. It was released after 380,000 years after the Big Bang, and when it was released, it was glowing in infrared. That means it is very energetic. But now when we observe this radiation, it has reduced its energy, and now it is in the form of microwave radiation. And it's kind of, we don't know where the energy goes. It's just destroyed. And we can also look at the way like energy of a photon given by Planck's constant times frequency. Planck's constant is a constant, it cannot be changed. That means frequency is changed. That means it has to travel. The frequency is also decreased. The frequency decreased. The space between the photon is expanded. That means the photon with the space is actually expanded, and that's why the wavelength is also increased, and that's why frequency is decreased. So the energy is destroyed. We don't know where it goes, but it's just destroyed. Energy is not conserved in general relativity. But that does not mean when we say energy is conserved, we are wrong. I mean, kind of, but energy is always approximately conserved in all of our day-to-day experience. Because the closer the object is to us, the less speed it is moving away. Hence, we can approximate the space around us to be static for small intervals of time. But in huge timescales, energy is not conserved. But people have redefined energy to make energy conservation work in Noether's theorem. One of the try is the Landau-Lifshitz pseudotensor. By incorporating the universe's gravitational potential energy to offset the gains and losses of energy in the universe. In short, energy is approximately conserved in all the situations we have to deal with. But in huge time intervals, energy conservation would not work because our universe is changing with time. That from this we can obtain that we can get energy from nowhere and can be lost to nowhere. In the case of the dark energy, we are constantly getting more and more energy. As the universe is expanding, the volume of the universe is also increased, and hence dark energy in turn. And we will come back to dark energy in an upcoming episode. So I'm leaving the details for that episode. But we will also talk about this thing in the dark energy episode. Okay. So energy is not conserved. So let's take a summary of all of this, a recap. Thanks for watching. If you want to know more about energy, you can watch my previous video on this channel. I'm giving the links in the description and also in the I button. Thanks for watching. See you next time.